let's extend that and we can talk about, we did velocities, let's try to understand it a little more and then we'll talk about acceleration. Okay. Now, if you look at the manipulator Jacobian, right? The manipulator Jacobian is a posture-dependent matrix because it's a function of Q. Q is the manipulator joint displacement. So as Q changes, the Jacobian will change, right? Because this is a posture-dependent matrix. So if I change Q, J of Q will change, okay? So for example, you can have J of Q1, depending upon what posture it is, J of Q2, and so on. In the simplest case, we studied that when you have a 2 degree of freedom manipulator, even though they reach the same point P, X, comma, Y, because the posture is different, you have different configurations, elbow up and elbow down. If this is the posture Q1, this is the posture Q2. Even though they reach the same point, the Jacobian is not the same. So J of Q1 will not be equal to J of Q2. Okay? Even though they are reaching the same point, the solutions are different, the postures are different. So in this case, you will not have the same Jacobian. Now this is a very simple case, but it makes the point that the Jacobian will change from point to point in the workspace. Now, let's look at a Jacobian matrix for n is equals to 6, right? So, if you have J like this, how many columns will this Jacobian have?
6.
Each column will be for, you'll have, if there are 6 joints, there will be 6 columns. Okay? I'm not talking about Z0 and O0, that will be 7. Okay, because you have frames going from 0 to n, that means you'll have n plus 1 frames. We're not talking about frames, we are talking about the number of columns in the Jacobian. Okay. So these columns each represent one of the joints in the frame, in the manipulator. Now, if you look at this, we also know that J is equal to JV and J omega. Right? So, you can write this as eta will be equal to J of Q times Q dot, right? So, eta will be equal to linear velocity and angular velocity. Okay? That will be equal to J of Q times Q dot. Or we can write V omega will be equal to, here we'll have JV and J omega. Okay. Now, let's take this example here, okay? Now I'm going to use this expression here. I can say V omega will be equal to, we have this matrix which is J1, J2, J3, J4, J5 and J6. Here we have Q dot. Q dot for a 6 degree of freedom manipulator, n is equals to 6. Let's say that this is Q1 dot, Q2 dot, Q can be either theta or D. This is if it's a revolute joint, this will be theta dot. If it's a prismatic joint, it will be D dot. Alright? So when you look at this, you can say that eta equal to V omega will be equal to J1 Q1 dot, J2 Q2 dot, J3 Q3 dot, and so on. So this is how it will multiply with each of the joint velocities to give you the end effector velocity, right? Now, when you look at this matrix here, so this will be same as Vx, Vy, Vz, because we want velocities in 3 directions. Same thing, omega x, or you can write this as, if you want in terms of Euler angles, phi dot, theta dot, and psi dot. Orientation velocities, right? So here you can represent it like this. Now, for the manipulator to have the ability to generate velocities in any given direction, all these columns of the Jacobian should be linearly independent. So what does that mean? That means if the manipulator is able to generate velocities in any given direction, in any, let's call it arbitrary direction, then all the columns of the Jacobian should be linearly independent. If they are not linearly independent, that means they depend on one another, and I'll give you an example of that. As we saw in the case of a singularity, it becomes hard to generate motion in one or more directions. So the way we check whether the columns are linearly independent or not is we calculate the rank. Okay, we call rank of the Jacobian. When you have a Jacobian, let's call this as R, rank of the Jacobian, we'll call it as rank of J. This will give you the number of linearly independent columns. If rank of J is equals to 6, all right? If rank of J is equals to 6, that means this is a fully conditioned Jacobian.
Professor, again, what is the rank of Jacobian?
Rank is the number of linearly independent columns. So for example, if you have the matrix like this, if you have column 1, column 2, column 3, you reduce the matrix to make sure, the idea is to make one of them dependent on the other and make one of them 0. If one of the columns becomes 0, what happens is when you reduce the matrix, if one of them becomes 0, you are left with 2 independent columns. Okay? So, depending upon the posture, if J of Q, let me write this as J of Q, because the Jacobian keeps on changing from posture to posture. If in a given posture, the rank is 6, that means it's called a fully conditioned Jacobian, or we also call it a full rank. Okay? A full rank Jacobian. When the rank is full, we'll try this out in MATLAB when we do the rank of the Jacobian. When the rank is 6, it's called a fully conditioned Jacobian or a full rank Jacobian. In this case, again, as we mentioned here, the end effector can have any arbitrary motion or any can have all right. Now, what happens when the rank is less than, usually the rank of a Jacobian, in this case we are considering n is equals to 6. Okay? So the maximum rank any matrix can have is the rank of a Jacobian will be always less than equal to minimum of 6 or n. Okay? Why is it 6 or n? So for example, if you have a 2 degrees of freedom, the minimum of 6 and 2, this will be less than equal to 2. Okay? So the full rank in this case for a 2 degree of freedom manipulator, the full rank is 2. It's not 6 because you're taking the minimum of 6 or this. So for example, if it's a SCARA manipulator, the minimum of this will be, SCARA is a 4 degree of freedom, so this will be less than equal to 4. Okay, so if the rank becomes 4, that means it's full rank, okay, for a SCARA manipulator. If you take a 6 degree of freedom manipulator, 6 DOF manipulator, 6, 6, so this will be 6. So when the rank becomes 6, that means it's full rank. In the case of a SCARA, 4 is a full rank. In the case of a 2 degree of freedom manipulator, 2 is a full rank. If you have a 3 degree of freedom manipulator, 3 is full rank for a 3 degree of freedom manipulator. Right? Let's say I have a 7 degree of freedom manipulator. What is full rank in that case?
7.
6. Minimum of these two. What is the minimum value? Why is it limited to 6? Why is the maximum rank that you can go up to is 6, not 7? Why? Let's go back to the first class. We discussed this. Why is, so here we can understand. See, I have only 2 degrees of freedom, right? This is the manipulator, right? So the rank can be only 2 because I have only 2 joints. I cannot have a third rank because I cannot generate motion along the third direction. I can only generate motion along 2 dimensions, right? Same thing with 3 degrees of freedom. When I have 3 degrees of freedom, the maximum directions I can move in is 3. Same applies to 4. But when I go to 7 degrees of freedom, why is the rank, maximum rank limited to 6? Huh? Any answer? Why is it limited to 6?
Because there are only 6 variables.
Exactly. You only need 6 independent variables to define the motion in 3D space. 3 for positioning and 3 for orientation. If you have a 7th or 8th degree of freedom, it's a redundant configuration. The joint is redundant. For a non-redundant configuration, that means any non-repetitive joints, any non-redundant will have 3 positioning joints or 3 positioning degrees of freedom and 3 degrees of freedom for orientation. Right? 3 for positioning and 3 for orientation. If I want to add one more, I can obviously add, but it will only add to one of the 3, either here or here. It will be a repetitive, it will be a redundant joint. Anything more than 6 will add redundancy. Greater than 6 will add redundancy to the configuration. So, the maximum rank that we are looking for is 6. When you hit a rank of 6, that means you can move in any given direction. That means you can generate any position or any given orientation. When the rank becomes less than full rank, so when the rank is less than this, is less than minimum of 6 or n, right? This kind of a configuration or this posture is called a singular position. a singularity. What do we mean by a singularity? Singularity is a posture where the rank becomes less than full rank. Okay? So singularity is a posture of the manipulator where the rank of the Jacobian is less than full rank. Okay? For a 6 degree of freedom manipulator, that means rank is less than 6. Okay? If the rank becomes less than 6 for a 6 degree of freedom manipulator, that means it has gone into a singular posture. It is really important to understand what a singular posture is, because when you operate a manipulator, you're trying to move it, and it becomes difficult to move the manipulator when you reach singular positions. Because when we said that when the rank is full rank, you are able to generate any arbitrary motion in any direction, whether it's orientation or position. When the rank is less than 6, motion in one or more directions becomes impossible. Okay? That means you are not able to generate motion in one or more directions when the rank becomes less than full rank. I'll give you an example. We have a configuration like this, right? We discussed the wrist. This was the wrist configuration. Okay, we'll talk about a wrist singularity. This is an example of a wrist singularity. All right. Now, this is a spherical wrist. So a spherical wrist is basically like this, right? You have 3 intersecting joints. This is the second joint. They're all at one point, the wrist center, as we discussed, right? So this is motion along this. This can be motion along. Okay, so we have motion along all 3 independent axes, x, y, and z, like this, and like this, right? Because these 3 axes are oriented like this. If you want, you can assume this to be in this direction. So it will relate to this thing. Okay, so now you can rotate this wrist, and you can have phi, theta, and psi along all 3 axes. So it's a completely spherical wrist. Okay, so this is one posture of the Jacobian. Let's call this as J of Q1. What happens when I orient this part, or the second joint, like this? Now, if I want any motion along this, what I do? I turn this joint, and I can have the wrist go like this, and like this, okay? However I can rotate about this point, and it will rotate the end effector like that. But when this becomes 90 degrees, what I have done is I have moved this to like this I have displaced this by 90 degrees. Right? I have moved it to 90 degrees. Now the joint comes here. Like this. Can I have motion in this direction? Even if I change this, it's not going to change anything, right? I've lost the ability to move along this direction. So this Jacobian, J of Q, will be less than 3. The rank of this will be less than 3 because I cannot generate motion in one of the directions. Okay, I've lost the ability. When this angle is equal to 90, the rank of the Jacobian will drop from 3, it will become 2. So you have only the ability to move along 2 directions. One direction is this, the other direction is this. Whether I move this or move this, it will only move along 2 directions. It's not going to move along a 3rd dimension. So in this case, it will help you when you move into a position, it will tell you in which directions you are able to move henceforth. So this is an example of changing the orientation. Let's talk about a case where you are unable to move in a positioning direction. Okay. So let's say I have a 2 degree of freedom manipulator like this. Theta 1, theta 2. X, y. Right? If I change theta 1, theta 2, I can move along any, let's say I move it like this. I go here and I move here. Y1, call it anything else. So any change in theta will change x1, y1, or anything. Let's consider, let's say that this is A1 and this is A2. Okay. Now what I'll do is, I'll make A2, this angle theta 2, I'll make theta 2 0. What happens when theta 2 is 0? When theta 2 is 0, the configuration will be like this. Straight. Okay. Theta 1 does not matter, theta 2 here, this is theta 2 is 0. This is A1. A2. Once it is completely extended, can I move any further in this direction? No, right? You can't go any further. When you are here, in this direction, you can move further or you can move inward. In this case, it's at the boundary. The only option for you to is move inside. You cannot move outside anymore. So moving outward is limited. You can apply an infinite force, but it will not generate even a small change in x or a small change in y. Nothing can create a change in x or y in spite of applying any force that you want or any torque you want. If it's a revolute joint, it's a torque. If it's a prismatic joint, you apply forces. So in this case, boundary condition here at the boundary of the manipulator, the rank of the Jacobian will drop to less than 2. Because you cannot move in one direction. When it is within the boundary here, you can move in both directions. You can move in x and you can move in y. It has full rank here. You can go in both directions. But in this case, you have lost. So this is an example of a arm singularity. This is anything that relates to positioning is called an arm singularity. This is called a wrist singularity. Okay, so you can find out at what points orientations are not possible, and you can also find out at what points in the workspace the positioning part becomes, or moving the manipulator, generating linear velocities along x, y, or z becomes impossible. Now, how do we find a singularity? What is the condition for detecting a singularity? So the necessary and sufficient conditions.
Excuse me, in this one, we have arm singularity because we can move along one direction, yeah?
You can only move inwards. You will not be able to move outwards anymore.
Yeah, but here we have two motions.
Yes.
So, why we call it wrist singularity?
You have 3 joints, right?
Yeah.
So the Jacobian has 3 columns, J1, J2, J3, right?
Okay.
So the full rank is 3. Full rank is 3.
Yeah.
That means I should be able to move along 3 directions, but I'm only able to move along 2. So it's less than full rank.
Okay.
Full rank is this, minimum of 6 or n. N is 3, right?
Okay.
Right? So anything that is less than full rank will be a singularity.
Okay.
All right? So in this case, full rank is 2. Okay? So, how do we detect a singularity? The necessary and sufficient condition for a singularity is the determinant of Jacobian should be equal to 0. Okay? If the determinant of a Jacobian is equals to 0, that means that this is a singular posture. So when I calculate the determinant of the Jacobian here, you will find that det of Q is equals to 0. So let's take this example. and find out at what position a 2 degree of freedom manipulator will be singular. So we have the determinant for we have the Jacobian for a 2 degree of freedom arm. Okay, so J for a 2 DOF, let's take a 2 degree of freedom planar manipulator. So here J will be equal to okay. Now find the, in this case we need to find the posture of the manipulator. Or let me write this, find the singular posture of the manipulator. Alright. So what you need to find is at what values of theta or theta 1, theta 2, determinant of J of Q equals to 0. Okay. So if you have a matrix like this, A, the determinant of A is, tell me at what values this is equal to 0. This is the determinant of A. So apply this here and tell me what you get. What is the value of theta 1 or theta 2 for which it is 0? So multiply these two and multiply these two. So determinant of J will be equal to AD minus BC, so we'll take this as minus, I'm going to take this whole thing. And finally we'll have plus alright. So these two will cancel. So you have A1, A2, will be sine of theta 1 plus theta 2 minus theta 1. So this will be equal to, so your determinant of the Jacobian for a 2-degree of freedom manipulator
Professor, why the rank of a Jacobian is important?
because it will tell you whether it's a singular posture or not.
So what?
That's what I explained. I said when you are in a singular posture, you cannot move the manipulator.
Okay.
You cannot move the manipulator in one or more directions. So when you're operating an industrial arm, if you happen to cross one of these points, you'll get stuck over there.
Oh.
Because you can't move from that point in one direction. You have to move out from the other direction. Okay, so when you're path planning or anything, if you want to get into one of these positions that you're unaware of, and you end up there, then you cannot move out of it. Okay, so if you are like this in a boundary condition, right, like this is a simple thing to understand. I mean, you can visually tell that you cannot move anything any further here, right? But if it's a high degree of freedom manipulator, or if there are joint limitations, in this case you assume that theta 1 is completely revolute, which is from 0 to 360. That does not happen in practice. Joints are limited, so you have theta 1 will have a minimum angle. Theta 1 maximum, okay? So for example, this is a 2-degree of freedom arm, right? When my arm is here, I'm more dexterous, I can move in any direction closer to my body. If I move forward, I cannot move any further, right? Even if I want to pick up something that is away, I can't move any further, right? So it is visually easy to understand in some geometric configurations, but when you go to 6 or 7 degrees of freedom, somebody who is operating this or designing a path planning application cannot tell if this is a singular posture or not. If you look at the wrist, you have 3 wrists, right? Like this. 3 joints here, right? Technically, this will give me motion along 3 different axes. But if theta 2 becomes 90, as I showed you, right? And I'm trying to generate an angle in this direction, it will never happen. I want to move it in one direction because my software tells me that I have a spherical wrist that I can move. But you cannot move no matter what unless you change theta 2 and then move it, then you'll change the orientation. But if theta 2 is 90, no matter how much you change the third joint to get a roll, you will not be able to do it. Okay? So it's really important to understand what positions you will not be able to generate motion in. Okay. So in this case, so this will be singular when determinant of J is equals to 0. This will give you singular postures. Okay. So when I apply this to A1, A2, sine theta 2 is equals to 0, what do we get? This will only be 0 when theta 2 is equals to 0.